And welcome to the Evidence Reasons Academy. I'm Salvador Cordova. This is going to be a nerd, gruesome torture session. It's the cross we have to bear for our Lord and Savior Jesus Christ, those among us who are both amateur, professional researchers, and students of science. You know what I mean. I don't have to go there. If you're a student of science, you know this can be just grueling and tough and tedious. It's not as fun as video games, that's for sure. And I love video games. I love watching sports. So I'm as fun-loving a guy as anyone else out there. So there are some people that just love this stuff and they just can't wait to get to it. I'm not one of those, never been. It'd make my life easier if I did love this stuff, but so much for complaining. So it's been like a week and a half at least, maybe even 2 weeks since I've done one of these torture sessions. A lot has happened in the last 2 weeks for me personally. Lawsuit, involved in a lawsuit, lots of legal proceedings, and there's just a huge amount of writing and researching involved in contacting and calling people. I'm getting just swamped with all sorts of calls, and probably at the worst possible time, everyone's wanting to get a hold of me and talk to me. And since I'm a nice guy, it's hard for me to just tell people to buzz off. So I might need to do that politely, of course. And then last but not least, I really, I have to be, trying to move forward in research. The publishing's been doing great. I'm pleased to announce I have been invited to sign a very minor television deal. And maybe by the end of the year, I'll be doing quasi-regular broadcasts on a particular network. And as that materializes, God willing, I'll keep you posted. I'm also working on a book, and at the worst possible time, people are asking to have me on their channels and to debate, and that's why I said I just some days just want to say buzz off. Where were you guys when I wasn't as well known? So that's just kind of how it goes. This stuff is just not easy. There's just no way getting around it, and it's just the notation dealing with electromagnetic theory is brutal. In physics, electromagnetic theory has been traditionally and notoriously viewed as like the most difficult. Now, to be honest, every field of physics, you could make it as hard as you want. You could take anything, classical mechanics, quantum mechanics, relativity, plasma physics, solid state physics, and just make it as brutally miserable, difficult as you want. But traditionally, where they really, if you're going through a physics curriculum where they really want to pound, it's just, I guess, been a tradition, is in electromagnetic theory. What makes it particularly difficult is you're dealing with 4 dimensions and at least 3 spatial dimensions, and the math just gets ugly as a matter of principle. It is a very well-established field. You can imagine what life would be like without electricity, and given that, you could just see how important it is. And how about radio waves and cell phones, etc., and microwave ovens? Just imagine if we had to live life without all of that. What makes it possible is electromagnetic theory. And having studied, I'd like to say I studied electromagnetic theory. It's more like crawled through it and continue to crawl through it. Compare that to evolutionary theory, there's just like no comparison how much a real theory like electromagnetic theory is compared to evolutionary theory. We don't, kind of in the extreme ends of physics and theoretical, there might be, some question of how it behaves. But for like definitely everyday electromagnetism, there's just not a lot of, debate about what it means and what we'd expect it to do, and how physical systems should operate under electromagnetic theory. It's because of the high reliability and predictability, and it's battle tested. We're confident that we could build things like radios, microwave ovens, and cell phones, et cetera, build computer chips, motors, generators, you name it. Electromagnetic theory also covers the optical spectrum. It helps us understand the nature of light, at least the wave nature. Yeah, we know about the wave-particle duality. So we could say kind of the wave nature of light is very well described by electromagnetic theory, and the particle nature somewhat by quantum mechanics. The kind of the packet nature. So if you want to understand light, you study electromagnetic theory for the wave nature of light, and then quantum mechanics for kind of the particle, the quantum nature of light. You compare that to the garbage of evolutionary theory. I'm just sorry, there's just no comparison. Just no comparison. In evolutionary theory, you just have all these claims. Most of them are completely unverifiable, and they're just storytelling, and we can't use evolutionary theory to build anything of significance, to the exclusion of other theories like common design versus common descent. So sorry to just be on a rant there. That just kind of gets me going a little bit, because this is going to be painful, guys. So this is partly done going through all of this, these papers in detail, is also for my own benefit, but it gives me a chance to invite other people to suffer through it with me. And let me try to get this lined up a little more. So I have to move my camera when I'm doing this. Because this is an electromagnetic theory paper and not a biology paper, there are just so many terms. There are so many terms and symbols that just take a long time to get through. So, for example, when I was studying electromagnetic theory, you get this, and we'll go through this. You'll see symbols like R, theta, rho, and you're like, holy smokes, what does this mean? You just get these symbols, and then you just get more and more symbols, and you have to memorize how it will map to a physical object. Its description of a physical object. So you have to say, okay, what does R, if I look at this globe, what does R mean? In terms of the coordinate system, what does rho mean? What does theta? And in navigation, pilot navigation, maritime navigation, we'll use words like latitude, longitude. You don't even generally think about R. But so there are all these terms. There's lots of trigonometry. There's a lot of multivariable calculus. And then in this paper, they started using, Russell Humphrey started talking about Reynolds numbers, and that's aerospace engineering and fluid mechanics. I'm just like, holy smokes, this is going to be, could be pretty miserable. So since Paleologos is here, what I mean by evolutionary theory, I'd like to say evolutionary biology. And there's a distinction between evolutionary theory and universal common ancestry. I do make that distinction. Evolutionists don't like to, because they love the conflation, because they think when they can prove patterns of similarity and nested hierarchies, they can explain the evolution of complexity. And yet in Darwin's Origin of Species, chapter 6, he mentioned, he talked about the origin of organs of extreme perfection and complication. And see, that's distinct from common descent. You can assume common descent, but then how do you explain the emergence of complexity, particularly, and now that we're going to the cellular and molecular level, where do these new major protein families come from that are integrated and complex? I mean, they just sort of kind of poof into existence. And gradual pathways are not indicated. And I've tried to make that argument in numerous places. I've also said you can claim universal common ancestry for eukaryotes and prokaryotes, and one scenario is a eukaryote came from a prokaryote, and it just ends up being a miserable mess when you realize that you might have to invoke miracles for universal common ancestry to work. So what do you do then? Because if stuff just kind of pops out of the air, so to speak, how's that really different than creationism? You can evoke, I mean, it won't be exactly young earth creationism, but you have this progressive creationism where you have miracles along the way, and that's something Michael Behe noted. So thank you very much for that question. And now we're going to delve into the miserable physics side of creationism. And I know that's what you all were so excited for. But guys, okay, let me just back up since it's been so long since we've done this. If we can prove the Earth is young, universal common ancestry is gone. Even the evolutionists will admit it. And some people have said you don't even need to have 100% proof. You just need to make a credible argument. And in a debate I had with someone who's just obnoxious, condescending, bullying, kind of dismissive guy, Ph.D. Tony, but otherwise fair, at least and knowledgeable, he kept harping on radiometric dating. And the problem is it's subject to a lot of cherry picking. You have lots of examples where it fails, and they just stick to the ones that seem to agree with what they're wanting to claim. But then I tried to point out all this contrary data. He was dismissive of that, not surprisingly. And I thought they were weak dismissals, but he put on good theater. I'm a lot more circumspect. He wasn't, so he just acts like he knew it all, and he doesn't. But I did notice he didn't deal with electromagnetism. Now, some people in the comments have complained that I wasn't covering the other side. I'm not going to. You can look it up for yourself. You know what the mainstream is. This is a chance to hear a creationist viewpoint, and I'm giving this more airtime because hardly anyone gets access to this. There's plenty of people that'll say, look at all the magnetic field reversals over history, et cetera, et cetera. And just need I point out, if they're saying it reversed millions of years ago, there's a little bit of circular reasoning to begin with already. So creationists argue there have been magnetic field reversals and changes in the magnetic field, but the time frame is wrong. One thing is, if the magnetic field erases in 1600 years, even in my lifetime, it's already decreased, say about 36%, something like that. I mean, 3.6%. Whew, it's getting late. 3.6%. It's already decreased 3.6%. So you could just extrapolate that. If you go linear, it's not going to be very. It's in about 30 of my 30 times my age, the magnetic field's gone. You can also argue from an exponential decay. However you want to cut it, it's going to be gone in 1600 years. The dipole, the magnetic dipole component. And we'll cover what a magnetic dipole component is, what I think it is. And I may misstate it. Anyone's welcome to correct me. But presumably a magnetic dipole is you have a north and a south. If you have variations in that field, you can kind of model it as if you had other kind of poles, like we call quadrupole, octopole. So instead of just north and south, you can kind of imagine that there is 4 other points on here, and you can kind of give them poles and intensities, and you can go quadrupole, octopole. I actually don't know the distribution of that. But if it's nice and smooth, if the magnetic field is nice and smooth and you have north and south pole, it's just the dipole. When you have kind of variations in that, you can make a superposition of all these other things like quadrupole, octopole, etc. I think any electromagneticist or electrical engineer can correct me, is it's kind of like when you're doing Fourier transforms. You have a waveform, but you can decompose it into sine waves of varying amplitude and phase. and just do a summation of that, and you can reconstruct, you can decompose it into these quote-unquote components. That is just a mathematical abstraction. It's a philosophical question whether it really is a summation of all these. Okay, I'm not going there. So I think that's the case with, you know, dipoles, quadrupoles, octopoles, and, you know, n-pole numbers. So that's the justification that we're going through this paper, and this is part 4, and now I'm just gonna be slugging through this also for my benefit, and maybe a little bit for the benefit of anyone who wants to be tortured through this. But this is a taste of professional creationism, and I just want to show this is really good stuff. This isn't the shallow stuff you get from most internet channels, like well, I'm not going to mention those. But this is where the battle is won, and I noted Ph.D. Tony's silence on this. It's like, okay, that's telling me this is problematic. This is also a testable prediction for the Earth. If, you know, it may exceed our lifetime, but certainly civilization will get a feel whether our magnetic field really is decaying. I think Russell Humphreys made a very good case that it shouldn't have been lasting very long, just going from basic physics. And this would also hold true for other magnetic fields from other planets. So there are numerous indications of the youth of the solar system, and also that the solar system was specially created rather than evolved from the nebula. And that's my feeling. And do we need 100% proof to make it, to believe it? I'd say no, because look at people who believe in abiogenesis. They have no proof. They need astronomical belief in overcoming astronomically remote improbabilities, and they still believe it. And some of them invoke multiple universes that they can't see. So, like, what's the difference here? Except we actually have a testable prediction about the trajectory of the Earth's magnetic field. We all, you know, the creationists also have a testable prediction about the decay of genomes, both human and elsewhere in the biosphere. It would be far more consistent with creationism and a miraculous origin than evolutionary theory. So people are saying, well, we want a lot more proof. I'm just like, you got to be kidding. You don't apply the same standards to your theories. So that's me on my soapbox, and occasionally I need to rant a little bit about this just to get me riled up enough to just make it through this, to suffer through this. This is a cross to bear. Glory and honor to our Lord and Savior Jesus Christ as we bear this cross for you students of science, and God bless you for suffering through this. So let's get to it. So we have current in any theory. All right, so this is where we are. In any theory, from simple considerations of electromagnetism, the electric current in the core causing the dipole part of the field must be similar to the toroidal current for a freely decaying dipole field. Okay, that is thick. Let's just make sure I got this right. Toroidal. So a toroid, I believe, is a donut. So speaking of which, there you go. So let's look at this toroid. All right, so now I'll go back. Electric current in a core causing the dipole part of the field must be similar to the toroidal current for a freely decaying dipole field. Okay. Toroidal current. So does that mean the current goes like this? I'm trying to think. I think it has to go like that in a donut. The toroidal current kind of goes in this donut. So you have a current flowing here, and according to, okay, magnetic current, and okay, this is where it gets a little funny. Okay, so there we go, the right-hand rule. So if we have a current going through a wire like that, I is usually the symbol for current. We'll get a magnetic field circulating like this, according to the right-hand rule. So if we have a toroidal current, let's say we have current going this way, according to the right-hand rule, so we have a current kind of going like that, briefly, tangentially like that. Using the right-hand rule, the magnetic field would circulate like this, and therefore you would get a pole. Okay, all right. So now let's go back to here. So just imagine electricity going through that donut, and we don't know the origin of that donut, but we'll model it like a little donut, and these electrons, the electron current is moving through this donut, and I don't know why it has to be a freely decaying dipole field. You could just, I think that is unfortunately gratuitous. You could just say a freely, a current for a dipole field. The electric current in the core causing the dipole part of the field must be similar to the toroidal current for a dipole field. I don't think you have to add a freely decaying dipole field. That's just my thought. I mean, you can put that because unless the current is going through a conductor that's a superconductor, it's going to slowly decay unless there's a means of maintaining it through that toroid. So this is where I really wish I could sit down with Russell Humphreys, Dr. Humphreys, and say, Doc, can we just sit through this and make sure I totally understand how this is working? So, but anyway, this is what I think. It's going to go through a toroidal current, means we have electricity flowing like this. So let me go back to the globe. So we have a globe like this, and you can imagine a donut kind of around, kind of inside a donut where the donut's lying on the same plane as the equator, or approximately. Now this is going to be very interesting. How do you reverse the magnetic field if you have a donut? So you have this donut inside the Earth, it's going to flip, so you could reverse the magnetic field. I'm just saying, how's the magnetic field going to reverse? Take any theory you want, any theory of the Earth's magnetism that you want. I just want you to appreciate how difficult it is, how much tectonic or geo whatever earthquakery that has to go on to flip an entire magnetic field. Because if you have a torus, or however you shape it, and it's generating the magnetic field of the Earth, you're going to have to flip that. You're going to have to do something kind of cataclysmic, I'd say, to flip an entire magnetic field. You're either going to flip the donut or suddenly reverse the current going the other way. How do you want to do that? The other thing is, as we pointed out, it is not axis symmetric. The magnetic North Pole is right here near Canada, this part of Canada. It's not exactly at the geographic North Pole. It is kind of like here. So this thing's wobbling. How are you going to have something wobbling inside the Earth and then it's going to flip? So I'm going to grant the creationists say we think the magnetic field is reversed. Not really reversed, it's really flipped. It's decaying and it's flipping back and forth. I got to say, this is not a trivial problem when you consider the scale of what has to be flipped around to make this work. So I think, you know, people say, well, that theory seems crazy. And it's like, well, look at the secular theories. Are they any better to explain how you can get a magnetic field of an entire planet to reverse and also to wobble? That's pretty impressive, something of you know, planetary scale and size that has to be kind of moving and flipping. I'm just saying, I don't think this, I think people are kind of trivializing how difficult it is to, one, postulate how this is generated, second, how it is sustained, and then also how does it wobble and then flip. I mean, I don't think these are trivial problems. I mean, if I had a magnet, yeah, it's easy for me to just flip it around, but how does that happen in the context of an entire planet? I mean, you'd need some titanic movement if you're actually flipping stuff around down there inside close to the Earth's core, where there could be, how are you going to, or inducing a total reversal in the direction of the current, how are you going to do that? So if you had a magnetic reversal, are you taking this toroid here, wobbling it or flipping it? Or are you going to invoke that suddenly the current started going the other direction for some reason? I mean, this is just like not trivial. So it's anyone's guess, but I've given a testable prediction, 1600 years. And I want to thank Mr. Jetty89 who sparked my interest in this, actually, because he sent me a video. Mr. Jetty sent me a video on the ozone layer as contributing to climate change, and the ozone layer is being depleted because the magnetic field has been decaying. The magnetic field decays, it doesn't steer the solar wind as strongly away from the Earth's atmosphere. Therefore, it hits the Earth's atmosphere, particularly the ozone layer, hits the molecules there, gets them to escape velocity, so they're out of the gravitational influence of the Earth, and they're gone forever. And there's this song by Alan Parsons Project, it's gone forever. Anyway, so, all right, we got through one sentence. This is not unusual for electromagnetic theory. We got through one sentence of understanding how this works. This is why electromagnetic theory is so miserable. Okay, starting from Maxwell's equations, Thomas G. Barnes, a creationist physicist, he was at Texas A&M, calculated the field, so that's a secular university, calculated the field and current distributions for free decay. For convenience to readers, I reproduced his results here using spherical coordinates r, theta, and rho. R, theta, and rho. Okay, so let's try to, I brought a, okay, I'm going to kill the torus here. I have a picture of spherical coordinates. So we had the Cartesian, let me go here. We had the standard Cartesian coordinates, x in the positive direction going this way, and y in the positive direction going this way, and then z in the positive direction going that way. But that corresponds to also, so if we have a point in 3D space, we can say x, y, z, but also we can also say rho. Where's that 5? Oh, did I say rho? I need to go back to my Greek letters. I am so, okay, that is a phi, not a rho. Okay, I know why. Sometimes it's rho theta phi, but instead they make it r theta phi. All right. I apologize to the readers if I were saying rho. Just so I know that I'm not losing my sanity. Rho theta phi. Yeah, some use the rho theta phi. There it is. Some have the convention of rho theta phi. Instead, in Wikipedia, it uses r theta phi. Okay. R is the distance from the origin. Theta is like a latitude. And phi is like a longitude. Oh boy. Okay, so this is confusing. And just let me do a comparison contrast. In navigation, you really don't need R because you just assume the Earth's surface. You just need latitude and longitude. I mean, you might say R kind of may correspond a little bit to distance above sea level. Okay, so that's sort of like an R, not exactly, but close. I mean, you could add sea level from the Earth's core, however number of thousands of miles, and then you add just a few feet. So it's kind of like an orbit. For the most part, it's just ignored, unless it's really important where you're stating your latitude, longitude, and altitude above sea level. So that's, you know, with a little tweaking, you can make it a spherical coordinate. But a lot of times, you know, unless you're really interested in kind of the aviation aspect or the elevation above sea level, you don't state R. So I'm actually saying this to help teach myself. I think you have a 0 latitude here. You have 0 latitude at the equator, and as you go up, it's positive 15 degrees, 30 degrees, 45, 60, 75, finally 90 at the top. So latitude is like ladder. You're going up, you know, from south to north. And let me just see how they do this. It's been so long since I've done aviation navigation. I think they say like 15 degrees south. They don't go negative. Right, so I'm now doing a comparison contrast. You look at the spherical coordinate system, and theta is not stated going from the equator, so to speak, from the plane of the XY axis. It's stated from going from the Z axis like that. So you go from 0, I think. Let me see how they state it. Okay. So we have conventions. Let me go through this. It's worth it because it's been like, all right, guys, it's been 30 years since I've had electromagnetic theory. Be easy on me a little bit. Okay. Some authors use rho for radial distance, phi for inclination or elevation, and theta for azimuth, and r for radius from the z-axis, which, okay, so there are conflicting conventions. So theta goes from 0 to 180. And the azimuth is often restricted to the interval minus 180 to plus 180, or minus pi to plus pi in radians. Okay, everyone has their conventions. Oh boy, what fun. Even with these restrictions, theta is 0 degrees or 180. Oh boy, I'm just going to be miserable here. Okay. This is, I'm going to hate. This is when I start to hate life. Because everyone has a different convention. All right. So I have my electromagnetic theory book here, and we'll see how they do the conventions. So they have cylindrical coordinates, and they have, here they have the one like in very close to Wikipedia. So I'm going to just try to read this. The second coordinate is an angle theta between the z-axis and the line drawn from the origin to the point in question. The surface theta constant is a cone, And the two surfaces, cone and sphere, are everywhere perpendicular along their intersection, which is the circle of radius r sine theta. The coordinate theta corresponds to latitude, except latitude is measured from the equator, and theta is measured from the quote-unquote North Pole. Okay, I'm going to uncoil this. This is just miserable, because they added a lot of extraneous things in this description by William Haidt of Purdue University, Engineering Electromagnetism, 5th edition. And that tells you how long ago I taken this. So let's go back to this. Let's go Brandon and go back to the spherical coordinate system. So what they're saying is if you had a constant theta and everything else is variable, you'd generate a cone. I don't know why they had to put that, but if you just say theta equals this, and then r and phi can be anything, you'll generate a cone. So let's say we wanted to have a function of f of r theta phi, and it equals, and the function is theta equals some number. It'll generate a function that looks like a cone in 3D. So remember, in 2 dimensions, you get a line, and in 3 dimensions, yeah, in 2 dimensions you have a function that kind of gives you a curve. In 3 dimensions, you can generate, oh wait, hang on. In 2 dimensions, you can generate a function that gives you either a line or some sort of plane, you know, a shape, a filled shape like a rectangle. And then in 3 dimensions, you can build even more, like something like a cone. Okay, I'm just thinking through this. So just munch on that. But the important thing, sorry this is confusing, electromagnetic theory is not easy. Neither is classical mechanics, because it's just getting the coordinate systems right. So theta can go from 0 to, all right, so let's see what Haidt has to say. The third coordinate, phi, is also an angle and is exactly the same as the angle phi of cylindrical coordinates. Okay, that's another thing. There's a chapter earlier on cylindrical coordinates. It is the angle between the x-axis and the projection in the z equals 0 plane of the line drawn from the origin to the point. It corresponds to the angle of longitude, but the phi increases to the east. The surface phi is a constant plane passing through theta equals 0, or the y-axis. You know, when you read this, it's just like, holy smokes, what are you saying? And it would be easier if we actually had like a animation and he could actually describe that and you'd see it. So poor old us, when we were studying electromagnetic theory, we had to actually visualize all these 3-dimensional objects in our head, because it's really, really hard to draw it on a 2-dimensional blackboard. Yes, and I was back in the days when we used chalkboards. So going east, this is called going east. We go, let me just make this bigger here. So going east, we're going from the x to the y, and we're going about the z. So as we increase the number of phi, we're going from like 0 to pi over 2, and back here to pi, and all the way back to 2 pi here. I think that's how it's done. And theta goes from 0 to like pi. So this would be 0 to pi over 2 to pi. And the important thing, and I remember this distinctly, the electromagnetic theory professor he said, nope, Sal, you went from 0 all the way to 2 pi. You only go from 0 to pi. just from north to south. You don't go all the way back north. In contrast, you go east and you keep going east until you go back from where you started. In terms of how, the range of numbers. And now I feel kind of bad. I would have gotten an A on that particular exam if I'd remember that. So yeah, okay. This is okay. We didn't even go through this right here, and it's taking a while, but this is important. Okay, so let me just verify that I got the range of this correct. Let's see if it gives the ranges. I wish they had just mentioned it here. I guess it depends on the application. Okay. So theta goes from 0 to 180. At least I saw it there. Yeah, I'd say that's a little bit of a deficiency in this book. The theta goes from 0 to 180. It wasn't explicit in this book. No wonder I got that wrong. I'm kind of upset about that now. So let's go back to the Wikipedia entry and just get this correct. So we can, yeah, that's the also obnoxious thing. They switch between radians and degrees and just have to deal with it. So we go back to conventions. The angles are typically measured in degrees or radians. Okay. And so that's the problem. We're going to be converting with kind of like the geographical coordinates that pilots and maritime people use to the electromagnetic coordinates. It's going to be confusing. I'm just going to bash my head. So on top of the problem with geometry, you have all these conventions you have to convert in your head, and I hate that. So they have negative radial distances. Okay, a common choice is R is greater or equal to 0. Theta is between 0 and 180, starting from the North Pole, and 0 to 360 for phi, starting at the x-axis. Okay, I'm just going to go with this until told otherwise. And this will be important when we start doing the calculus, which is going to be just miserable. This is why electromagnetic theory is hard. You just have to do all this accounting. It's more, there's a lot of conceptualization, but there's a lot of accounting, and then there's a lot of unit conversions and conversions in terms of the conventions being applied. All right. So now let's move to the next sentence. All of the current is in the, hang on, let's move to the next sentence in Humphrey's paper. All of the current is in the azimuthal east to west direction. All right, so what does he mean? So we have this little donut in here, inside our globe. And as we go, like say, from the United States east to west, I'm sorry, we go from the United States from the east coast to west, said east to west. So the electric, okay, this is going to be miserable again. In electrical engineering, we use positive charges rather than electrons. So current goes kind of these hypothetical positive, net positive charges going from positive to negative, even though we know the electrons are going from negative to positive. That's just been a convention that's been adopted. The United States Navy, in some of its publications, tried to go back the other way and just ended up confusing things, because then you go to electrical engineering books, it talks about positive current, you know, positive charges, and you're just like, say what? You don't have protons moving. It's like, okay, that's just the convention. You can it's adequate enough for our purposes. So the quote unquote positive charges, if I'm reading this right, are going from east, like say from Washington D.C. to San Francisco to Japan to China to Israel to Spain and back to Washington D.C. Or in this case, we could go down to say Peru and go all the way to Malaysia, and then the Congo, and then back to Peru. So that's how this positive current is circulating in that toroid. So just trying to visualize this. This is really important that we visualize this, because then you can see it in your head. So just imagine that donut inside and the current's flowing around like that. This is why electromagnetic theory is so miserable. It just takes so much to set it up. So then its density in amperes per square meter is this J phi. And we have this term X, which I was pretty upset with, but they'll explain it. It's defined here. And then we have R, and we have theta. So you see that the coordinates here are theta, phi. So we have J phi. We have a theta here and an R. Let me think about what this means. What to do. I'm trying to visualize this. So X is this thing called pi times R over RC, where RC is the radius of the core. So R over R core times pi equals X. So we could substitute for X something that has an R term in it, times some constants like pi over RC, R times pi over RC, R times pi over RC, R times pi over RC. So then we get this J of theta, the current density, in terms of just R and theta. So at any point of R and any point of theta, we get a current density. I'm going to have to try to think about what this means. So let's go back to our spherical coordinate system. So if we have a given theta, a given phi, the current density for a given phi and an R. Okay, so we're getting a current density, how much electricity is flowing. So let me go back to that toroid picture. So if we take a slice out of that toroid, we can also have coordinates in terms of R and theta, and each of those positions would have a current density. And I'm just trying to think about that. I think that's an instantaneous current density for a given theta and R. And that would be electrons per square meter. Okay, so now let's go to the definition of current density. Okay, told you this is going to be brutal. We're not even through. We're hardly even through a paragraph. We're going to slug through this. In electromagnetism, current density is the amount of charge per unit time that flows through a unit area of a chosen cross section. The current density vector is defined as the vector whose magnitude is the electric current per cross-sectional area at a given point in space. The current is whose magnitude, okay, its direction being the motion of the positive charges at this point. Remember I told you okay, so let's go back to this. The current density vector is defined as the vector whose magnitude is the electric current per cross-sectional area at the given point in space. Its direction being that of the motion of the positive charge at this point. In SI units, the electric current density is measured in amperes per square meter. Amperes per square meter. Can we have a current density at one point? I think you can have a current, at each point you have a current density. So then to get the number of amperes, you integrate over the area, and then you get the total current, which is I. Okay, so yeah, you have to integrate it in 2 dimensions, and then you can recover the actual total current going through the slice in the toroid. So I wish I had kind of these, if I could just kind of visualize, I mean, just imagine taking a donut and you take a knife and you slice through the donut, you take a slice, it'll look like a little wafer. And I don't mean to be irreverent. I was going to take a communion wafer, that'd be so irreverent. So let's say we slice out a piece from that toroid. So just imagine then that I take the, go back to the toroid, let me make this bigger. So let's say I take a slice out of this, you know, I take a knife and I slice one little slice out of that donut, and I end up with a slice that's like that out of the toroid. So then that has a cross section. It has a cross section, and I can get the total current here in terms of the amperes. But at each point, I could say there's a certain number of amperes per square meter at each point. That's the current density. So that would be what they call the J phi, the J phi, I think. Let's go back to there. So J phi, so for a given phi, let's go back to spherical coordinates. Okay, so for a given position on the toroid, we can at each theta, for a given theta, I mean for a given phi, when we get the rest of the coordinates, theta and r, we're able to compute the current density in that slice. So the slice, let me go here. So the slice, I could take a slice here that would correspond to a given phi, and then another phi would be a slice here, another phi would be a slice here, another phi would be a slice there. Now I'm going to anticipate something, and electrical engineers out there might appreciate this. Since we might assume that this is mostly the conductivity is the same at all points. In this toroid, we can use Kirchhoff's law and say the current going at one phi is also equal to the current going through another point or any other slice of that toroid. So you could just, this J phi is probably J phi for almost all phi approximately. I'm just going out on a limb here. and applying Kirchhoff's law. So you electrical engineers know what Kirchhoff's law is, okay? So there's this mu is the magnetic permeability of free space, which is 4 pi times 10 to the minus 7 Tesla meters per ampere. Oh boy. Okay, we've been going almost an hour, and maybe tomorrow we'll cover these units of what magnetic permeability is. And then we'll cover this equation here. This is not for the faint of heart or putting brain to the mind. This is not for the faint of heart or putting brain to the mind to get through some of this. So we just have to kind of do this piece by piece. I mean, if we are doing a homework problem on this and you're a physics student or engineering student, this is how much you'd spend an hour just going through the geometry to conceptualize it, just to get all your terms. That's not unusual. I mean, I remember a physics student saying he's taking electromagnetic theory and he's saying that's like a full-time job. He was just like so miserable because you're just doing stuff like this. You're just trying to understand what the terms are in the symbols in the equation. You're just trying to visualize, what does that symbol mean, you know, in terms of, you know, when we're thinking in terms of spherically. And there's a story of where these guys were taking electromagnetic theory exam and they're doing the right-hand rule, and you could see them in the middle of the exam that they're kind of going like this or like that, trying to visualize the problem that the professor was giving them, and they're trying to solve it. It was really almost I wasn't there to witness that particular exam. You could just imagine guys in the middle of an exam using the right-hand rule and kind of doing, you know, stuff like that. And there was even right-hand rule in the electrical engineering classes. So this is, as brutally as we've slugged through this, I think we've made headway trying to understand what the problem is, how Humphreys is describing his model for how the magnetic field is generated. But then you also in the process realize this, whatever model you come up with, if you've even have the mainstream one, it's not going to, you're going to have to account with some problems of how things are going to do a field reversal. I think any explanation of the field reversal is going to be, you know, there's going to be a bit of outrageousness to it. It does happen. Everyone accepts it. But, you know, how much has to happen inside the Earth for a magnetic field to flip? I mean, I can understanding it flipping kind of slowly, but then you have this, you know, the problem of axis symmetric fields, and why will it follow the Earth's rotation and then flip? I actually think it's really, if you have something that's circulating, you have gyroscopic action that you have to overcome. I think that's kind of hard. I don't think you can just flip a gyro very easily. I think you can. Let's see. Yeah, no, when you have a bicycle, the bicycle, it doesn't move laterally easily, but I think you can turn like the steering wheel on the bicycle, you know, the front wheel. I don't know. It's been a while since I've done that part of classical mechanics. I'm just saying that these are all considerations we have to take if we're going to invoke magnetic field reversals, kind of the physics involved of it. I think it's going to be a headache. And I don't think it would be, I think any mechanism that could actually flip something that big is going to be really, really interesting. And, you know, I think that's why the creationists would argue that it would have to be kind of a cataclysmic event to be able to flip something, you know, of planetary size to flip the magnetic field. I don't think it can be easily done just with simple electronics to just reverse that much electricity in the Earth's core to go the other way. And not to mention you have the wobble. So, okay, so this is really good electromagnetic theory, if nothing else. Hopefully we've come away with this, learning a little bit more about spherical coordinates, and I've gotten reacquainted with it. And let's see what's coming up. We'll just do more trigonometry, a little bit more just understanding terms like what a Tesla is. And so thankfully, we'll just go for 3 pages like that, maybe 4, before we get to the serious stuff where we have these del operators and cross products. Oh boy, Maxwell's equations. So we're 4 pages away from the really miserable stuff of electromagnetic theory. Thank you for bearing with me, and if no one else watched, it was still a lot of fun just knowing someone might watch. And I've been blessed to know that there's someone out there who might be remotely interested in this, viewing it by recording or something. This is what serious creationism is all about. It's not for the faint of heart or the pudding-brained of mind. And so glory and honor to our Lord and Savior Jesus Christ, and for helping us bear this cross today. And I'm gonna now, let's see, I'm going to close out with the usual Rachmaninoff. So everyone, brothers and sisters in Jesus Christ, be blessed, and till next time, Lord willing, God bless you.